So we're going to continue to look at refraction in triangular pieces of plastic, and at this point in time I'm going to draw sort of a very peculiar piece of plastic, which is what I'm going to do is I'm going to go bang, bang, bang. And so I'm going to make a right triangle like this. Okay, and so this is my right triangle right there. So I got a 90-degree angle right there. And what I'm going to do is I'm going to have a ray of light. This is going to be simplified, but because there's going to be complicated things that come out of the choices that I make. And this is a good one to pay attention to. So I'm going to have a ray of light that comes in like this. And you saw how I drew it. I set up my protractor like that. Okay. So one thing that people will do that I see very, very often, so this is wrong. They will look at this and they will go, okay, N1 is 1, theta 1, let's see, N2 is 1.6, and theta 1 is 90 degrees. No. Angles are measured off normal. So normal is perpendicular to a surface. So I measured this so that it was perpendicular to the surface. So how far off of normal is it? Right now, my theta 1 is 0 degrees. Now, I'm not going to do the calculation, but I think that if you sort of look at it on your calculator, I want you to calculate. So this is n equals 1.6. and on this side n equals 1. I want you to calculate very quickly what the angle of refraction is going to be when it goes into the block. Okay, if you hit pause and did it, you would see that since my angle of incidence is 0, my angle of reflection or refraction is going to be 0. And so the ray of light is just going to go straight like that. So now I have a new normal over here. And I measured that this ray of light, let's figure out the best way to measure it. This ray of light is 45 degrees. Wow, shocker that. I didn't have to measure that. I could have told you it was 45 degrees. So now, let's do some real Snell's law. I've got my N1, since I'm inside the glass, my N1 is 1.6, my theta 1 is 45 degrees, my N2 is outside of the plastic, and so it is 1, and then I've got theta 2, so I've got theta 2 is equal to sine inverse of N1 sine theta 1 divided by n2. So I get theta 2 is equal to sine inverse of 1.6 sine 45 degrees divided by 1. So I do that on my calculator. Sine inverse of 1.6 times sine 45. And I don't need to divide by 1. Oh goodness, what just happened? Okay, did I type something in wrong? It says error, quit domain. Well, I'm a little bit confused. Until, of course, since I have a master's degree in physics, and I've done this for a number of years, and so I'm actually lying to you, I'm not confused at all. I realize that 1.6 times sine 45 is 1.13. But the largest sine theta can be is sine theta must be less than or equal to 1 and greater than or equal to -1. Must be. So I can't take the sine inverse of 1.13. So sine inverse of 1.13 does not exist. Well, so what happens? Basically what it means is that with this angle of incidence, the angle of refraction would have to be greater than 90 degrees. But if the angle of refraction was greater than 90 degrees, it would be back inside the glass, and so it wouldn't undergo refraction at all. So we have just found total internal reflection. Because Snell's law breaks down, it means that we're going to have total internal reflection. And what that means is if it came in at 45, it's going to undergo our basic law of reflection, which is really simple. Angle of incidence equals angle of reflection. And so it's going to go out at 45 degrees. And so the ray of light is going to go this way. And so this is total internal reflection, number 1. Well, gosh, I'm really stacking this problem. That is parallel to that. Watch this. If I make a new normal, then this is going to be, well, it should be at 45 degrees. If that's parallel, well, it should be. I haven't quite drawn it just quite parallel. Oh, I'm sorry, I gotta go up here. There we go. There's my 45 degrees. So then this is 45 degrees, and that means that it's going to undergo total internal reflection again, and it's going to bounce down at 45 degrees, and I'm going through this quick because I'm running out of time. And so here, theta is going to equal 0 degrees, and it's just going to come out the same way that it came in. Okay, so this is a corner reflector, And you should really know more about corner reflectors. I'm probably going to spend some time in the next video talking about them.